Cool. So, hey everybody. How you doing? Some new faces. Good to see you. So this is part 2 of data structures, and no need to have seen part 1. Part 1, we worked on implementing a stack from scratch and a doubly linked list. Those are both over here, just creating some classes. We identify what the primary operations are on the particular data structure, and then go through and implement it. And lots of data structures to do. There was some interest in doing a hash map, which I think would be plenty of fun. Is there any other particular data structure that folks really want to get to?
Whatever you think is the most important.
I'm still in the directed graph.
In the what?
Directed graph.
Directed graph. Yeah. I think the directed graph, I think let's save that at least for after the hash map. I mean, in some ways it's not like a super complex data structure. Usually what you'll do is a 2-dimensional array of, that's like an edge list. So you've got your nodes over here and the same list of nodes over here, and if there's an edge from one to the other, you put like an X in the box. And if there's an edge from the other to the first one, you put an X over here. Like it's, and that's basically it. But I'm happy to talk through that with you, and if there's interest in the group, we can go through that. But let's do a hash map.
Was there a particular reason why you did a double linked list versus one linked list?
We've talked about linked lists in phase 3. It was like last week or the week before. So it just made sense to do something else. I think somebody mentioned wanting to do it. Cool. So let's start off with what is a hash map? What are we talking about here? Okay. It's like a JavaScript object.
But my understanding is an object of objects.
Okay. I might nuance that a little bit. Who wants to see if you can define what a hash map is? Yeah.
Yeah, I'm not 100% sure, but yeah, like Sal said, it's like an object. My understanding is it just has like key value pairs, like a dictionary itself has an arbitrary key, and every key has whatever value you decide to assign to it.
Mm-hmm. Bingo. A hash map is an object that contains key value pairs where the key is something that is hashable. And we'll talk about what that means in a little bit. But hash map is the kind of data structure-y word for it. You'll hear people talk about that when you're talking about data structures and algorithms. But more commonly, like in JavaScript, there is a map, and that is actually more technically a hash map. In Python, it's called a dictionary, and I'm sure there are plenty of other words for this. But that's what it is. Key value pairs distinct from an array, which is a mapping of indices within a certain range to a set of values. This is, you can look something up by any hashable value. What else? So the operations. What are the operations that you can do with a hash map? Okay. What else? Okay, add, remove.
Look up in a key value pair.
Mm-hmm. And I'm going to call that search for right now, and you might see why.
We can also insert, like, doesn't have, instead of adding to data, we can insert a specific place at a specific point, which is a little bit different than add to the end of the hash map.
So I don't think so. One of the properties of a hash map is that it is not ordered in any particular way. If you were to display a hash map there are no rules about in what order you display keys and values. It's just a sort of abstract collection of key value pairs. So it's not numerically ordered. It's not alphabetically ordered. There are some implementations of hash maps where they will say, we guarantee that we maintain insertion order or something like that. But that's not, I think, an essential property of it. The essential property is actually that there is no particular ordering. And so there would be no, at least for this case, there would be no particular place to insert something because it's just this big pool, right?
Do you also want to check if it's empty or not?
Sure, you could do that.
Update keys value.
Okay, update a keys value. Say it again. Yeah, so length, both empty and length are kind of getting at what is more commonly just get keys. So you can do that with JavaScript objects, you can do that with maps, you can do that in Python with dictionaries. You can get a list of all of the keys. And that would be, if you wanted to iterate over a dictionary, that would be the way to do it, is get an array of the keys. So then you have something that's ordered, and then you can just look up each thing as you go. Make sense? So let me pull up Big O cheat sheet. So you guys see this okay? So here are a bunch of data structures, and you can see the kind of comparison of time complexity for each. It's interesting to look at the hash table or hash map. I suppose I can put that as another hash table, is another way we refer to it. If you have an array, for instance, you have an access operation, meaning give me the thing at this location. Give me the thing at index 1 or index 5 or index 1000. You can also search, meaning search through this array for the thing that matches what I'm sending you. Why do you suppose it is that a hash table says NA for access?
Because certainly the value is more valued by the actual value itself, instead of pointing to the position of the value. There's no, like you mentioned, there's no certain order. So you don't need to access the location of the value, just access the value.
Okay. Does that make sense to folks what Sal said? John, you have kind of a crinkled forehead.
Well, I was going to say just because it's not recognized, you don't have the emphasis, so you can't use that. An object, you just access the key.
Yeah, it is kind of a funny thing. Like in an object, you can just access the key. But the thing to kind of take home about hash maps, like, you know, one of the things that you should take away from all of this is that the primary operation with a hash map is a search. It just so happens that a hash map is ideally suited to searching, and so you can do it in big O of constant time, big O of one time. But when you are putting in a key and getting a value back, while that seems like an access operation in the same way that we access for an array, you're actually just doing a search. You're saying search through this hash map for this key and then give me the value. Cool. And so why are we talking about hash maps? Why are hash maps so cool? Why do I always get that, like, this grin on my face when we talk about hash maps? Because big O of constant time for all of the operations. Whereas an array, you've got big O of n time for search, insertion, and deletion. So even though an array is ideally suited to some things, you know, you've got this like very notable thing that if you have an array of 10 million objects, your worst case runtime is a function of that 10 million rather than constant. Cool. So how do we do a hash map? How do you implement a hash map? Let me ask a question first. When we say hash map, what does hash mean? Okay, store. What did you say? Okay. Mm-hmm.
The difference between the key and the hash value, because usually hash value is like 1, 4, 3 or something. I don't know. Yeah, that's what I.
Uh-huh.
But there's a hash function associated.
Yeah. Anybody else want to share how you define a hash function? So hash functions are real important, and you know, would not otherwise expect you to know about them. But the more you know about them, the more you'll understand what underlies blockchain, Git, like security. Bcrypt is a one-way hash. So without trying to kind of come up with some like really great definition on my own, I'm just gonna see what the.
Objects are king.
Say that again.
Objects are king.
Objects are king.
I don't know, heard it. So I'm guessing that's why you always have this grid on your face. It's like objects are the best.
Yeah, well, that's sort of true. So a hash function is any function that can be used to map data of arbitrary size to data of fixed size. Values returned by hash function are called hash values, hash code, digest, or simply hashes. And then it talks about hash tables. So that's it, is you can do a hash of a file that's 1,000 lines long and hash that to a string of characters that's 64 characters long. You could also hash a file that has 1 character in it, and you would also get a 64 character hash. And this we have utilities for this. So let's see if I can blow this up. I think I have. Let's see. What I had. Okay, so like MD5 is kind of not in vogue anymore, but this is a hash function that you can use on any number of things, including files. So if I hash this README, it gives me this hash value back. And that hash value is going to be the same as long as this file is the same. And if I do a different file, it's going to be a totally different hash value. And you see 0978C, this is F8C62. And we oftentimes interact with hashes as if a hash of one particular thing, no matter what it is always going to produce this like one unique hash value. And that makes it really, really useful for us. It makes it able to do things like when you create a package, say you create a library, you can create that package, put it in a zip file or something like that, and then take a hash of that. And when you send this file out to people, you can send them both the zip file and the hash. You can say, when you download this, make sure you run a hash of the zip file so that you know that you are getting exactly the same code that is the code that I compiled, the code that I wrote and put together. So we use it for data integrity, because let me open up, so code organization. I have some file in here that's code organization. and this is what it is. If I change one character about this, we're going to get a totally different hash, 0f068c99. And so you can imagine if you had a library and you did a hash of it, and somebody who was receiving it did that hash and didn't get the same value, it could be because just one thing is off, but it's important to know that. Like, you know, make sure that it wasn't tampered with. So yeah, and so bcrypt, another perfect example of a hashing function. Bcrypt actually is designed to hash multiple times. So you hash and then hash and then hash. And that's so that, but the principle is the same. One thing, like one password, always produces the same hash. So when you're checking a password, you can take that password and hash it. And if it matches that hash, you know that you're good. John, you have a question?
Yeah. How does this relate back to object keys, essentially?
Great question.
That's where my disconnect is.
Yeah, great question. So assuming we have a hash function, so we need a hashing function which takes some hashable value and returns a hash code of fixed length. Once we have a hashing function, so the way that we'll probably implement this is by writing a hash function that instead of generating a long string of alphanumeric and alphanumeric characters, we'll write a function that takes in a value and it'll take in a string and it'll output an integer. And that integer will just be within a certain range. So, so why are we doing that? Because once you have the ability to take a string of any length and hash it to an integer within a certain range, then we can make an array and index by that integer and put the value in that array. Does that make sense? So yeah. So we need to get from some way, we need to somehow get from a string, which you can't look up in an array by a string, to something that you can use to look up an array by. And so if we write a hashing function that takes a string and returns a number between 1 and 64, for example, then we can create an array that is 64 elements long, use the hashing function. So if we wanted to put in a key that's Justin, okay, we're gonna have our first thing in our hash map be key Justin, and the value is Haheim, my last name. You can hash Justin. That'll give us some number between 0 and 64. And then we can put Haheim in that array between 0 and 64. Wherever that hash function tells us is the hash value. Is that clear so far? Yeah.
Question: how would you handle collisions in this?
Great question. So you can imagine if we're doing something like this, where we're hashing from the set of all strings ever down to 64 like integers between 0 and 64, that at a certain point, probably won't take very long, you're likely to get what's called a hash collision. And that's actually true with really any hash function that I think it's basically an essential property of a hash function is that hash collisions are possible. Very unlikely, and depending on the hash function, very, very unlikely. But in our case, especially if we're going to do something like 0 to 64, it's actually quite likely. I mean, if we put in 64 different strings, the 65th would by definition need to have a collision with something. right? So not only do we want to use a hash function to put something in this array by the hash value, but we also need to have some way to handle when two things map to the same spot. Okay? And there are a couple different ways to handle that. I'm inclined, and give me head nods if you think this is a good idea, I'm inclined to have us live code together a hash function and get the map working. And then after we've got that working and we've kind of taken this like abstract conversation and made it into actual code, then we can start handling collisions. Does that sound okay? Yeah.
Also, I just want to mention that Breeze work at compliments this episode.
Yeah, I was planning on going to 2:30. Judy's, oh, the boyfriend talk, yeah. Who is wanting to go to that talk?
What is that talk? Right. Compensation.
Yeah, it's like how to make sense of and negotiate good like benefits packages, I guess, including.
Yeah,
Yeah, I think she's.
Just looking at this.
Well, I know afterwards she's going to do an AMA from 3 to 5 anyway, so if you can push it back by 15 minutes and just cut the AMA.
Yeah.
Would somebody be willing? Do we know if she's in a meeting? Is that
I
what?
think she's in the meeting.
Okay, John's on it. So in the meantime, we'll try to do this as fast as humanly possible. So
No bugs.
no bugs. Okay, so at 2, will you run and
Yes. I have a quick question.
what's that?
Before we get too far off, the reason why this is efficient, if we go to that big old notation cheat sheet, the array, accessing the array is all one, and then that's basically what we're doing all the time whenever we do any of these other things, right? So that's why. That's
Bingo.
the connection, right? Okay.
Yeah, and it's two things. We're using an array as the underlying data type to implement the hash map, so it's one of the data types. But also, we're using a hash function that is also constant time, right? So we gotta look at both of those because every lookup operation in a hash map is going to need to hash, and so it's exactly like you're saying. We're accessing an array and we're hashing the value, and both of those are constant time. Yeah.
This might be going a little bit deeper than what we're trying to do here, but why is an array access so much faster than everything else?
Trying to think of like a good visual metaphor. It's like a computer by definition can access any point in memory in what is effectively constant time. Like it doesn't take a computer any longer to go to memory value 0 as it does to memory value 256. And because an array is typically implemented like when we're getting down to the system level with fixed level, fixed length contents. So say we had an array of integers. Integers are going to be 8 bits long or something like that. If you want to get to the 50th thing, the only thing that you need to do is go to memory location 8 bits times 50. So you can mathematically calculate where that value is going to be because of this property of arrays that they are just this like fixed length thing. Yeah. Yes, it is. Right here. Cool. So let's start with a hashing function. This hashing function is going to take in a string in our particular example. Though in JavaScript, And in other languages, you can usually hash a string or a number, or sometimes you can even do slightly more complex data types. We're going to stick with strings. So what we want to do is take the string and return a hash value. And the way that I'd like us to do this is to take the string and look at the character code, like ASCII code value of each character, and add those up. This is not going to be perfect. This is not an ideal hashing algorithm, but it'll work for our purposes. Does that make sense what I'm saying? That, you know, if it's ABC, you look up the code for A, which is going to be like 61, and B, which is 62, and C, which is 63. And that will, when we add those up, that'll give us a number. So how do we do that? Somebody want to live code us through that?
I mean,
You can use reduce.
you have to split the string so that you could apply, or you could get each string's, like each character's ASCII value.
Okay, so string split. And I just learned this morning that in JavaScript, you have to put an empty string here. If you include nothing, it won't actually split it by character. Who knew? So,
Generate like one element.
yeah, right.
Yeah.
So we're splitting the string, and then what?
And then you can either, you could do a like a map or for each, I guess in this case, for each, right? And for each character.
So the for each takes the element, and we could actually, in this case, call element character, which would be a little bit clearer.
And so for each character, it's going to do character. Forget the syntax to it, but it's like from char code or to char code. I'm not exactly sure what the syntax is to get the as code at char code at. Yeah.
Is that what it is? That looks promising. Char code at. So we've got that.
So that will give you the number for that character, and so we want to have like a count, and so you would say count plus equals this char code at. Basically.
Plus equals character code at. Make sense?
Sorry, can you explain what character code at does?
So characters on computers are actually represented by numbers. If you look at like, I'm going to show you the simpler version. So ASCII code table. So ASCII is not used very much anymore. What we use is UTF-8, and I forget what that stands for. It, you know, back in the day, it used to be ASCII, and this was it's just a different table. And so the number, what is it? The number 65 was a capital A, and the number 97 was a lowercase a. And so you could look up any of the characters by this number. And so under the hood, a text file is actually just a sequence of numbers, right? And then to display it, you just look up each of those numbers and display the kind of glyph, the character picture that corresponds to that. And we use UTF-8 now because it's a much expanded set of characters. So it includes international characters and emojis and all sorts of stuff like that. So I actually believe our hash function would work for emojis. So keep that in mind. It's like kind of a tough group right now. Good. So why don't we just give this a try? Hash hello and hash goodbye. And we'll console log those. Make sure that they work, and I don't think I have anything else executing in this file. Lectures. Data structures. Okay, so we're going to run data structures. So 532 and 745. Pretty good? Good, so we've got a hashing function. Now, we want to actually create that, that data type. So we're going to make a class, and we'll call this my hash map. Have I been calling it a hash map? I used to call it a hash table, and I don't know why it changed. So we want a constructor. For you folks in P4, have you been doing JavaScript classes and constructors and stuff?
Working with React.
Okay, good. So what do we want in here? How are we going to put this, how are we going to hook this thing up? Oh, good. So we got till 2:30. Say that again. So we will be having them pass us keys. So we'll be passed keys in order to access this. But in order to construct the object in the first place, what is the underlying data type that we're going to use? Not an object. An array, right? Because we could make an array that's 1,000 elements long, and hello would go in element index 532, and goodbye would be in 745, right? So that's the kind of key thing here, is the relationship between a string, its hash, and the array that we're putting it in. And then we'll get into collisions later, which is kind of its own interesting question. So if we want an array, why don't we say this dot data equals new array, and let's give this a size. So this is an interesting part of hash maps. We could implement a hash map with an array of size 4, right? After we inserted 4 elements, we would be absolutely getting collisions, but we could still do it, right? Because there will be a way to handle collisions. We could also do it with an array of size 10,000. And if we did that, but we only had a hash map that had 3 values in it, it'd be kind of a waste of space, right? So you get the sense already that there's an ideal kind of middle point. You see that? We don't want something too big. We don't want one that's like 1 million long, but we also don't want one that's going to be getting a ton of collisions. Yeah?
Could that value dynamically change?
Yes. Yes. So a hash map could change its own size.
By deleting, by basically copying itself to another location and deleting the other location and adding things.
That would be one way to do it. Yep.
I mean, isn't it also possible, because JavaScript is really weird, you could have an empty array and then say array at position 738 equals this, and then it will just make 737 undefined, and then put that in position 738.
Yeah, so you're saying why pick a size up front? Why not
Why
just...
not just have an empty array, and then as we insert stuff, it will insert that spot as necessary.
Sure. Yeah, that's possible, but I don't think that buys us anything, and I think you'll see why in a minute. So for right now, I'm going to suggest that we do an array of, let's do an array of 32 elements. Okay, so this is going to be initialized as an array that's empty. I don't remember if it's null or undefined. So we've got an array of 32 elements, and can't think of anything else to do in the constructor. So let's do our insert operation. So insert is going to take an element, but I'm realizing it's also going to take a key. So we could call it key and value, right? Because anytime you want to insert something into a hash map, you need the key, which is its lookup, and you need the value, which is the thing you're looking up. So how do we want to do this?
Can you hear me?
Since we're working with an array, then to add to where you can use a push method to add to the array. And we'll dot.
Okay.
But
What if we keep the array of this same length?
I would then just like access certain things.
Mm-hmm. Yeah, John.
Do the hash map. It's not the how do I work it? Data at the index of the hash value of the key is equal to the value. But then yeah.
Bingo. That'll work. Except hash right now could be really, really, really long or really large. Like if we did hello, this is going to be a much bigger number than just hello on its own, right? So 9,576. So modulo. Yep. So does everybody know what modulo is? This is effectively how you get the remainder of a division operation. That's one way to think of it. So if you divide 5 by 2, it's 2 remainder 1, or 2.5. And so what we want to do is take this number, which could be 0 to technically as big as we want, and we want to confine it to a specific range. And I would log this in your brain because modulo comes up in a number of algorithms. Like it is one of the very useful keys to a lot of algorithms, you know, because it happens a lot that you need a number of some large amount to map to something a lot smaller. So if we did modulo 32, we're always going to get a number between 0 and 32. Is this making sense? So that's the effect for us, is that doing mod 32 is going to give us a number between 0 and 31, actually. So I want to forget how to do this in JavaScript. Can you define a static property? Can you do like size? Do JavaScript classes allow you to do that?
I don't think so, but I'm not sure.
I'm going to do something kind of ugly for right now. This dot size equals 32. And that way we're going to not have a bunch of magic numbers. You know the expression magic numbers? This is a good one to know. Like, you know, dry, don't repeat yourself. This is like the same sort of thing. Magic numbers are when in your code you have specific values that define something, but that like may change at some point. And ideally in your code, you don't want these values kind of interspersed throughout. What's much better is to have at the very top that value once, and then, you know, you can always change it up there instead of having to change it in the file. Or even better, sometimes you have it in an environment variable and you pull it in. So an example would be putting a port in your file. You might write port 5432 like a handful of times in your files, but then what happens if port 5432 changes to something else? So good to define a number like this once so that you can change it in only one place if you need to. So this dot size. And so now we can just do this mod this dot size. And that should do it, right? So what happens if we comment these out for a second? So if we take this function and our class, we go to the node REPL. Is this big enough? Visible enough? So paste this in. Okay, so const h equals new my hash map. So that's the JavaScript representation of our hash map right now, that class. And we've got a data. Data is an array of 32 empty items. So now if we do h.insert, and let's do what we had before, hello. Let's take a look at h. Let's take a look at h.data.
Wasn't it expecting a value too, besides just the key?
Oh, word. Yeah, oh, good. So we've got 20 empty items, undefined because that was the value we passed, and 11 empty items. Let's try this again and insert hello and Adele, because that was what popped into my head when I said hello. So there we go. 20 empty items, Adele, 11 more empty items. Why is it at index 21? Because that was what the hash came up with, the hash modulo 32. What if we insert something else? What's another Adele song? All right. We'll do goodbye. So we're doing goodbye, not Adele. And h.data. So we've got at point 10, not Adele, and 10 items later, 11 items later, Adele.
Justin, why is it on a cross-logging Adele's coming up, but why not goodbye or why not hello?
So because, probably because the node REPL doesn't want to display every single item. So we could do h.data.for or .map console.log, and that. Why didn't that work? Not Adele.
Well, aren't these just now indexed in an array, so they don't have key associated with it, right? The key is just used to access the array that's underlining, which has an associated index. So it's not going to print the thing that you put into the hash, right? So that is not stored any place, right?
I don't think I follow exactly.
So like when you put in, what is it, goodbye, that's going through the hash function.
Yep.
And then putting out an index for the array, which we are then accessing. So that's actually, that index before the hash is not being stored any place, in any location in memory. To access the value, you just have to be submitted and then get the value. Right?
Word. And we do need to store both the key and the value. And you'll see why. This has to do with collisions. The one thing that I was just trying to do is to help us visualize this is to just print out each item of the array. Console.log element. I wonder if this is going to do the same thing. Why is it?
Yeah, something where I guess it begins like 20 something undefined.
Yeah, I wonder if that's, well, it's so weird that it's doing that. For let I equals 0, I is less than h.data length, I plus plus, console.log h data of I. Let's see what this does. There we go. This is what I wanted. And we could actually do console.log I h.data. So there we go. That's what our array looks like. Pretty good?
Yeah,
so that's the insert. And we can, let's see, what should we do next? So you can imagine remove is pretty straightforward. We do the same thing, we hash, and then we just reset the value to undefined. All right, so let's skip that one. So we do have this operation get keys, right? With a hash map, you need to be able to get the keys, which means, as John was, I think, gesturing to, we need to be able to store the keys. So it turns out with a hash map, you need to store the value, but you also need to store the key as well. And that's because it's because of a few things. We need to be able to get the keys, but also if there is a collision, two different things that land at the same spot, one strategy for dealing with that is putting them both at the same spot. You find some way to put them both in that same element. And then once you index to that place, you just see, does this key match the first element? Does this key match the second element? Does that make sense? So if we put in something that also mapped to 20, we would want to have, what was it, hello and Adele, and then that other key and that other value in this spot. And then when we're searching for it, we can say, was the key hello? No, the key was this other thing, therefore we get that other value. Make sense? So
Is that still being then stored as, then you'd have to like have that stored as an array at that element, basically, so that you can, have more than one string.
mm-hmm.
Into that element.
Yeah, an array would be one way to do it. You could also use a linked list, and my hunch is that a linked list is the more common way to do it. It's a lighter weight data structure. Like, I don't know if you guys have seen, but in our implementation of a linked list, it's a class that has just 3, so this is a doubly linked list, and it has just 3 pieces of data to it. The data itself, what's next, and what's previous. And if it were just a singly linked list, which is what, when we say linked list, that's just what we mean. It just has the data and then next. So it's a very lightweight data structure. So probably the slightly easier thing will be to do an array. So shall we do that? Yes? No?
How would we store it? How would we even utilize an array if we have to store both the key and the values?
Good. So yeah, so there are 2 things going on here right now. Needing to store the key and the value, and let's tackle that first, and then needing to handle collisions, and let's tackle that second. So the first thing is we not only need the value, but we need the key. And so one way we could do that is to just store an array of 2 elements. One is the key, one is the value. So we could do our whole thing here again and just see. So const h equals new my hash map. And if we do h.insert, hello, Adele, h.data, right? So now each entry is going to contain both the key and the value. So that's that, but that also now we also have to tackle this problem of collisions. So how do you suggest we do that? I'm looking at the people behind the screen too. We've talked a little bit about how to implement it. We need an array or a linked list or something at the element, at the index. So
basically, the collisions that we have two values of the same index, is that different?
yeah, because again, if we put in 32 elements into this array, totally different strings, if we put in a 33rd element that had even still a different string, it would have to collide with something based on our implementation. And that's true of hash maps in general. All right, come on, Guildies. Somebody talk me through how we change this insert operation to handle if there's a collision.
Make it a linked list.
Well, let's use an array. We were just saying let's use an array for this now. We could use a linked list, but just for ease, let's use an array as that data type. But what do we need to do before we actually insert the thing? What do we need to do?
You need to get the
Length of the. No, you're doing great. See, this is the thing. Isn't Stephanie doing great for just volunteering an idea here? That's all we're doing. That's all we're doing.
So you want to see what's already in there, right? Like
Bingo.
32, so you want to see if there's anything there.
Let's check if there's something there. So so I'm going to take this little bit here, hash key modulo this size, and I'm going to put that here as const key equals const key equals hash key modulo this dot size. And this is just key, except I can't call it key, can I? Hash code. That's what we want. Is that clear? So if this dot data hash code has something in it already, then we want to do something. Otherwise, we want to do something else. And we know that if there's nothing in there, this operation works, at least for now. So what goes in here?
If there's something where you want to get the length of it.
What do you mean?
Or, well, if it's already inside, don't we want to create
Yeah. Yep.
I mean, could you also just not add to the already existing array the key and value pairs? Because an array could be, arbitrary length. So if you already have an array in there, you could just push the next key value into the end of that array. So
element 0 and 1 would be the first thing, and 2 and 3 would be the second thing?
Would be this new thing that you're trying to insert.
Mm-hmm. Yeah. Does that make sense to folks?
Is it like, I mean, it's an array, so you could just do array.push and you wouldn't have collision. I would just put it in.
Mm-hmm. Yeah. The way that we could structure this is, and don't let this get too confusing for you, but this dot data is an array, and that array has undefined, undefined, and maybe it has something here, which right now is the key and the value, and then it's got more undefined. So one solution is we could just do key value. We could know how many things were in there by just taking the length of this divided by 2. So that's I think a workable solution. Another solution would be make this an array of pairs. And I don't think there's any ultra compelling reason to do one or the other. So because multiple people suggested that we do this, I say we just do this. Cool? So if there's already something at this location, what do we want to do?
Data hash code dot push.
hash code dot push, and push adds on to the end.
So the first thing would be the key.
Mm-hmm.
And we repeat it with the value.
And then repeat it with the value. Does push return the array itself? Oh yeah, so we'll need to do two operations. So key and then value. Okay. How is this looking to you? So the fun part now is implementing search. So search takes a key, and what we need to do is get the value based on that key. So because we're at time, I'm going to publish this to GitHub, and I invite you as a challenge to try implementing search on your own. And I know you can do it. It's a little bit of a thing to wrap your head around, but I know you can do this one.
Is there a time complexity we're looking for?
Is there what?
Is there a time complexity we're looking for?
Yeah, so it should be constant time complexity. Big O of 1. Sound pretty good? Who's thinking of doing the challenge between now and Monday? Cool. That sounds good. When you do it, why don't you post it in the phase 3 channel? Because this is a phase 3 sort of operation. Post it in the phase 3 channel if you have a solution. Cool. Thanks, everybody.
That was really awesome. Just gotta say, that was really awesome.
Oh, good.
Demystified
Thank
hash
you.
maps like by a lot.
Good.